Actually calculating fluxes using integration can be challenging, so let's work through an example. Let's suppose we have some flat sheet sitting in the xy plane with dimensions h and w respectively. And let's suppose we also have some non-uniform E field given by a I hat plus bx j hat plus c y squared k hat. Let's take a moment to visualize what the field does so that we make good math decisions later. The I hat component of the field never changes. The j hat component of the field varies with x. And the z hat component of the field varies with y. Flux is E dot A if everything is constant, or integral E dot dA if something is varying. Let me take a moment to call out a misconception that I see from time to time that gets people in trouble. People often say that the thing that's being made differential is the thing that's varying, which in this case would mean that since the E field is varying, there should be a dE. But that is emphatically not true. The thing that shows up as a differential in the equation is the thing that we're breaking up into little pieces. Let's write that down and box it and put stars around it and never forget it. The thing that we have to break up into little infinitesimal bits for the sake of the integral is what we write as a differential. The E field doesn't get broken up. It has one well-defined value at every point in space, even if that value is varying. It's the area that's going to get broken into little chunks. Let's go ahead and get started. We'll calculate the total flux by writing down one infinitesimal bit of flux, which is the flux through a little chunk of the surface. That's E dot dA. Then we'll add up all the bits with an integral. We know that dA must point normal to the surface, so we'll let the dA vector be the dA magnitude times k hat. And now we can do that dot product. I dot k and j dot k are 0, and k dot k is 1, so basically we just end up keeping the component of the field that points through the surface. Now, how are we going to write that dA? Or, put another way, how are we going to break up that surface into infinitesimal bits? There are two ways to proceed, using either a single or double integral. First, the single integral. The whole point of integration is to take something variable and complicated and break it up into bits, such that everything is relatively constant on each little bit. The E field varies in y. So let's break up the area into strips that each live at one particular y coordinate. And the area of one of those little rectangles is h times dy. We're integrating with respect to y, and y ranges from 0 to w, so we have everything we need. And we get chw cubed over 3. Not too bad. The other approach is to use a double integral. Then we don't have to think too hard about how to break up the area. We just break it into a bunch of little squares. Each square is infinitesimal in both x and y, so dA is dx dy. We put it all together and integrate with respect to x, and then y. And in the end we get the same thing, as we should.